All right, so you were given a few online worksheets to go through, and let's consider these solutions. Let's see, am I able to write? Nope. So refer to the following information for the next 4 questions. A ball gains 30 joules of potential energy when lifted to the top of a vertical post. Some of these I'll be able to pull up in Smart Notebook and draw out for you, and some of them we can just talk about. How much potential energy will it gain if rolled to the top of an incline that is the same height? It doesn't matter how it gets there. As long as it reaches that same height, it's going to have GPE, right, of 30 joules, same height. Now here, 3 steps. They're equally spaced, which helps us. How much potential energy will it have on the second step? Well, think about the third step first, right? Here's 1, 2, 3. It's going to have 30 joules. If they're equally spaced, you have 0 joules, 30 joules. These must be 10 and 20 joules. So there'll be 0, 10, 20, 30 joules of gravitational potential energy. Because remember, it varies only with the height. And since the heights are equally spaced, then the grades, the the GPEs will change exactly the same way. So if it falls back down, right when it strikes the ground, really the moment before it touches, you should say, because of conservation of energy, it should have 30 joules of kinetic energy. Right? So started off with 30 joules of GPE, just like with the basketball drop, it will convert over all the way to kinetic energy by the time it reaches the bottom. 10 to the 4th joules, that's 10,000 joules. I was about to say 1,000, no, it's 10,000 joules. Make sure you keep your exponents in line. And so it's a massive steel container, this guy right here, initially lifted to a position so work is done against gravity, and it's given 10,000 joules of GPE. And it's going to drive this post into the ground. So you crank it up, you do work, and if you were to cut this, which means you release it instantly, then it should come down and drive this pylon into the ground. So how much work is it going to do on the post? Well, it's going to be the change in energy, right? At the bottom, you assume that it has 10,000 joules of kinetic energy that it's going to convert. Basically, it'll do work on the pylon, right? Kinetic energy related to work is the work energy theorem. Changing kinetic energy is work. So it should do the same amount of work as it was able to have kinetic energy at the bottom. A pendulum initially displaced to a height h, so it can go down this far. That's the ground level right here. So it goes up, and it's making its way over. It says it has the GPE, right, gravitational potential energy of 10 joules. How much kinetic energy is it going to have at each point? Well, we already know that it starts off at 0 speed, so 0 kinetic energy, and it's going to end up the same way. And they've even drawn it a little lower, considering it being a real situation, not an ideal situation. So there's some friction loss here, some air resistance loss. So the kinetic energy, once it stops, is going to be 0. Now, at these points, remember total energy is boring. Okay, total energy doesn't change. So if there's 2 joules of GPE here still, it means it still has a little bit of height left, then it's going to have 8 joules of kinetic energy available to it. So it's moving relatively quickly. Now it's moving at its fastest at the very bottom because all the gravitational potential energy has been transformed into kinetic energy. And of course we've already discussed this last half. So a ball is released from rest. Here's a semicircular ramp. And it's again the idea that total energy is boring. What's the gravitational potential energy here? Well, if we know the kinetic energy at the bottom was 50 joules, and that's the total energy, right? 0 plus 50 is 50. Since total energy is boring, and there's no kinetic energy at the top, right when it's released, then it must have been given 50 joules of gravitational potential energy to start with, so 50. And then at this point, because of the geometry of the semicircular ramp, it's not a straight ramp. At this point, we have 25 joules of gravitational potential energy, and so we have 25 joules of kinetic energy as well. Total energy is boring. Total energy does not change. It looks like the writing is missing here, but the idea is that you just need to figure out what the kinetic energy would be at each point. So 15,000 joules is our total energy, right? 0 plus 15,000. Total energy is boring. Whatever 15,000 is, minus 11,250, minus 7,500, minus 3,750, minus 0, will be 15,000 joules of kinetic energy at the bottom. This really shows that spectrum, that change. So as long as these add up to 15,000 joules, we know that we have found the correct kinetic energy. Because, again, total energy is boring. A car is moving at 30 kilometers per hour. It has 1,000,000 joules of kinetic energy, 1 times 10 to the 6th. How much kinetic energy would it have if it doubled its speed to 60 kilometers per hour and then tripled its speed? Okay, well, you don't need to think in terms of kilometers per hour. We like to use meters per second more. You could go through this and you could calculate each and every one, except you don't have the mass. So you could technically solve for the mass, convert the units and solve for the mass, but it's easier than that. You know the kinetic energy is 1,000,000 joules. If we double the speed, forget the 60 and the 30, if we double the speed, remember how it's related by the square law? So its kinetic energy is 1/2 mv squared. Well, if you double the speed, it's 2 squared, which is 4 times as much, so 4,000,000. If you triple the speed, there's 3 squared, which is 9 times as much kinetic energy, so 9,000,000. So it's simpler than it looks. It's all about the concepts. So far we've been able to talk these through, and it helps that the numbers are really not that difficult. But I think I'll pull these into Notebook. Let's see. Because they're a little bit more difficult to talk about. Bear with me here for a second. How much did I get? I got all that. Print screen. This way you have this to reference as well. Okay, that should cover everything. Yeah, good. All right. So a few calculations. How much work, and they emphasize the idea that it's energy, is needed to lift a 200 Newton object to a height of 4 meters? Well, work, force times displacement, 200 newtons is the force, 4 meters is that displacement that it's going to be lifted through, so 800 joules, which is why they emphasize that it's energy we're talking about. How much power is needed to lift this? Well, power is work over time. So it'll be 800 joules divided by 4 seconds. That'll be 200 joules per second, which are watts, 200 watts. And then just another calculation. What is the power output of an engine that does 60,000 joules of work in 10 seconds? Well, again, power is work divided by time. So just drop off a 0. It's going to be 6000 watts. 6,000 watts. Don't confuse the unit of watts with the variable for work. Now, block of ice is 500 newtons. They've actually done these in kind of a reverse order than what I would like. So let's talk about that. Let's just analyze this system. At the top, this box, it weighs 500 newtons, so that's mass times gravity, and then the height will be 3 meters. So it's going to be 500 times 3, or 1,500 joules. You really have to be careful, because if you're giving something in newtons, you just have to recognize that that's mass times gravity already. Because what you'll do is you'll end up accidentally putting 500 newtons times 9.8, and you'll screw yourself up, because it already is converted from kilograms to newtons by gravity. So 1,500 joules is the total energy that this will have at the top, the gravitational potential energy. So that should actually be how much work is needed. So you can see how it's a little out of order. And actually, it should be the same amount of work to push it up the incline. 1,500 joules, because total energy is boring. It doesn't matter how you get there, so long as you get there. It starts off with the same amount of energy at the top, one way or the other. So if you were to roll down again or fall down, it doesn't matter. It's negligible. It's the same exact idea. Total energy is boring. So now this one actually becomes a little simpler. If we take the work equation, work is force times displacement, then force covered up is work divided by displacement. We know it's 1,500 joules, which, by the way, is a Newton meter, and it's going through 6 meters. Okay. Meters are gone. Let's see if my math is good here. If it were 3,000, it would be 3,500, so maybe 250. 250 sounds good. And look, we have our little handy-dandy calculator just in case. Let me impress myself. Yep, very nice. So 250. There we go. 250 newtons. And that's the only reason I showed you here this breakdown. It's important to know that 1 Newton meter is 1 joule. That is the breakdown. 1 joule, a Newton meter. Also, if you're interested, a kilogram meter squared per second squared. That is a joule. Okay. And then as we move down, all the ramps are 5 meters high, so they're giving us a little bit of perspective here. From conservation of energy, well, duh, is all we're using, right? We know that the kinetic energy of the block at the bottom of the ramp will be equal to the loss of gravitational potential energy. So it's a transformation from GPE to KE. So find the speed. Okay, well, we only need to find the speed once, because they're all reaching the same height. And that fancy little equation that you found, square root of 2GH, well, it's going to be the square root of 2 times 9.8 times 5, which, you know what, I'm just going to pull my calculator out for that one. 2 times 9.8 times 5, square root it. Y root being 2. Okay, 9.9. 9.9 meters per second. And it's going to be the same speed no matter what, because it's reaching the same final point. So moving on, we have, again, the same idea. We have this block. It's going to reach the same level down the bottom. Which block gets to the bottom of the incline first? And which one arrives with the greater speed? Well, they should definitely have the same speed. So that's our first, initially. Why must they have the same speed? Well, because the kinetic energy at the bottom and the GP at the top are equal. Now, in order to answer the first part, which one gets to the bottom of the incline first, I like to use logic. And it's this idea that if I went to extremes and I compared two other situations instead, let's say A and B, if I had one drop down and I had one follow a path like this, I think I can imagine that the one that had a straight path down would reach it faster than the one that had to go a long ramp, or even, really, really long ramp into infinity or so. All right, I can see that, and it makes more sense. And you can look at it mathematically, but the idea is that A should actually reach the bottom first. My students tend to like that logic. And let me know if you found another way that you prefer. So either mathematically or logically, it works very nicely. So again, a two-energy transformation. We have gravitational potential energy, G, gravitational potential energy. So fill in the missing values. Well, its kinetic energy at the bottom is 75, so E total must be 75 joules. Well, that's really great because that means it's 75 here for gravitational potential energy. Must be 25 here. Must be 25 there. So you see again that spectrum as we go down. And then finally, for the practice worksheets, which I hope you found useful so far, we want to find the speeds. Okay, so they've brought us through, and we can again use speed equals square root of 2gh. Which is kind of why I introduced this to you, because it's such a nice little shortcut. So at the top, it starts from rest, so speed is 0. We know that. They don't even ask it here. And then they're showing this to be the 0 meter mark. And let's see, it starts from the rest at the top of the wire, showing us how fast is it traveling as it passes. So here's 5 meters. Now you'll notice that they don't ask us for the speed at point C, and that's good because we have no idea what this height is. However, I can tell you that it is traveling fastest there. This is just an idea of frame of reference. Technically, we could make this our 0 meter mark, but the problem has chosen not to do that, and it's just to show you the idea of frame of reference. You set your frame of reference, but it will be definitely fastest here, no matter where we set our ground level mark. So in reference to this, we don't need mass, right? That's negligible in this. It doesn't actually factor in at all. So the speed at B is going to be square root of 2 times gravity times height. Well, the height is the height through which it fell. And look how nice this is. They're actually going through exactly the same height. So no matter what happens here or here, it's frictionless again, right? So if we find the speed here, then we found it there and there. So once again, square root of 2gh, it's the same, basically. 2 times 9.8, and it's reached a 5 meter mark. And then square root that thing. Again, 9.9 meters per second. And I don't need to go back through each one because, as I said before, they're at the same height. If they're at the same height, then they have the same kinetic energy in the system. And if they have the same kinetic energy in the system, they have the same speed. And then finally, this little question here about wind turbines, basically. Does the power generated affect the speed? And the idea is actually that um, the speed of the wind is going to affect the speed of the turbines, which is going to affect the electric power generation. And then if we put turbines behind them, what would happen? Well, they're using a lot of that kinetic energy for the wind, and so they wouldn't be able to produce as much power, energy per second. All right, so that's your worksheet. Hopefully that was enlightening.